my dear student, colleagues, and all the viewers who are watching this program live from Facebook page, Physics Adda, I'd like to welcome you all in our International Physics webinar. Today it's our 42nd Physics webinar. So good afternoon to all here in Bangladesh and those who are watching this program live from Taiwan. So hope you are well and safe from Corona pandemic. So the whole world are facing a problem with Corona. So we cannot actually continue our normal academic program as the institution have been shut down since March 2020 due to the Corona pandemic. So we have to start our online program. So our department, I think you have come to know that our Department of Physics, Pabna University of Science and Technology, has started some online program. And in those program, we have online classes and seminar and webinars. So we are trying to adjust with the new normal, So in this new normal, we have to maintain some health rules and some other things. What the main aim of our International Physics webinar is? So the main aim of our physics webinar is to motivate and encourage our students in this Corona pandemic situation, as they are staying their home. So they may be frustrated with them by staying home, so far from the institution. So we actually think that if we arrange some international physics webinar, they may motivate and encourage, and they may know some new physics, some new research in physics, and they may interested in that. So today, I'd like to welcome you all to a joint session between Pabna University of Science and Technology and Research Center, High Energy Physics Group, Institute of Physics, Taiwan, in astrophysics. And we have with us here today Dr. Henry Tsz-King Wong, Research Fellow and Deputy Director at High Energy Physics Group, Institute of Physics, Academia, Sinica, Nankang, Taipei, Taiwan. And connecting with us from Taiwan through online, he has already connected with us. So good afternoon, sir. And
good
welcome
to
everyone. Our International Physics webinar. Actually, it's a very great day for our department, as we are witnessing such a wonderful webinar with you. So we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, because you accepted our invitation, though you are too busy with your research and other works. So for those who are new, I'd like to introduce that we have divided our webinar into three parts. First, I'd like to introduce our speaker with all of you, and then our speaker will deliver his piece with you. And at the end, we have a discussion session. In that time, anybody can join with us. So, and you can ask question by commenting. So I think this is a very good opportunity for our students and for the viewers who are interested in physics to learn new things. So you know that today's title is the Neutrino Physics, the Broad Landscape. And our speaker is Dr. Henry Tsz-King Wong, Research Fellow and Deputy Director, High Energy Physics Group, Institute of Physics, Academia, Sinica, Taipei, Taiwan. So if we see his educational background and research position, we can see he completed his BA in physics from the University of Oxford, UK, and PhD from California Institute of Technology, USA, and research position. So he was a research fellow at California Institute of Technology, USA, and Paul Scherrer Institute of Switzerland, and research fellow European Laboratory of Particle Physics, CERN, and Switzerland research staff physicist, CERN, Switzerland. And if we see his research interest, we can see his research interest is neutrino physics and astrophysics, astroparticle physics, particle physics instrumentation, luminescence, and cross-strait academic collaboration. So career experience, he was worked as a research fellow at California Institute of Technology, USA, and also CERN. So if we see his publication, so he has a lot of publication in the different journal all over the world, and we can see his Google Scholar ID, and you can see that his citation number is more than 5,000, and we can see his Inspire Help ID also. So we feel proud to host him in our International Physics webinar, and I would like to say thanks again, sir, for accepting our invitation. So thanks. You can start your session. It's your time, sir.
Yes. Okay. So thank you, Professor Das, for this very innovative and also very timely ways to do physics outreach to a much broader audience. We should make use of the tools of the internet, and COVID gives us both a chance and also an opportunities, despite the problems of going online and learn physics and meet people way beyond our immediate horizon. Yes. Okay. So so for today, I would be I appreciate the efforts and the invitations, and then I'll share with you some give you a very broad landscape painting of neutrino physics, which is my area of expertise. First of all, now I myself have to learn how to give online internet talk, because there's absolutely no response from my end. So there's no red light, I won't see I won't see the audience. So whenever there's some technical problems or something that doesn't go on smoothly or 100% well, Professor Das would please interrupt me anytime, and then we'll try to fix the problem. So we will start now. I go on full screen now. You should be seeing my full screen, like a PPT full screen, and then with a red laser pen. Okay, now so we start from this. Okay, so neutrino physics is my expertise, and it happens that there's a great progress in neutrino physics in the last 50 years, and this audience, I believe, is include a lot of undergraduate students who are not experts in particle physics in general, but well, with any experience, one can appreciate the beauty of science and the development. So I would try to give a very broad sketch without getting into the details, and but a lot of materials will be covered. Maybe maybe, and even to an exaggerated note is that a good portion of science would be covered in the next 1.5 hours. So there won't be a lot of details, but I hope that the students and those who are not familiar with it would get away from this room knowing that a lot of it has been done in science. It is an interesting subject. It is worth exploring more, learning more, or maybe some of you may wish to explore that in the future, to do more serious studies, and then entertain the idea that it can be a good career. But this 2 hours will not turn anyone into a professional. It can only hopefully inspire your interest and trigger a fire. So I would give for today, I will give a broad overview of not just neutrinos, but just standard model. What is the standard model of particle physics, including neutrinos? And I will focus on the story of neutrino properties, and in particular, the advances made on neutrino oscillation, one aspect of neutrino physics that is made in the last 40 years, 50 years. But I would not focus on all the technical details about how error bars are compared, but I would tell stories as well as the science. But in fact, along the way, maybe we can illustrate to some of you how science works, which is beyond neutrino physics. And then I'll beyond after this chapter, then of course there are some new projects, current projects, and then what are the future main goals and so on. So I would give a wrap up on this, again, very sketchy, but then just pinpoint that to let you stay tuned to your newspaper, to your science magazines, that what to look for in the future. So we proceed our journey for today. Yes. Okay. So standard model of particle physics. Particle physicists are basic. We study basic science. So what basic science? What do we try to learn, to understand? Now I start from the basics, and then is in terms of trying to reach a broader audience. So we try to understand these subjects. Try to understand the alphabet and the grammar of the universe. And indeed, we have made a big advances in our understanding. So in terms of the alphabet, the constituents of matters. What does the thing that surrounds us made of? So now we know at school we learned that from atoms made of atoms. Atoms are made of electrons, and the nucleus is made of protons and nucleons and neutrons, and then protons and neutrons are made of quarks. So these are the alphabet of the universe. And by now we know that there are 6 different quarks arranged into 3 families, and accompanying them is the 6 different leptons. Electron is one of them, and corresponding to each lepton family, there are 3 families, and there's 1 neutrino. So the quarks and leptons are the alphabet of the universe, and how they interact, they would be transmitting some force carrier, which is expressed in particles. It's a ZW, gluon, and gamma. Gamma is the photons, and then central to the picture is binding together is a elementary particles discovered some 8 years ago called Higgs as CERN. And together with this picture, this alphabet is an antimatter. So there's anti the electron, anti-U, anti-D. So the matter, and there's this antimatter. That is the composition of the universe. Yes. So how about the grammar? The grammar we mentioned that we know that there are 4 different ways to look at interactions. Interactions, they are gravity, weak interaction, electromagnetic interactions, which is light. When we point at what you are seeing, the screen is at the end electromagnetic interactions. The light gets to your eye. Strong interactions that bind the nucleus together, and that gives us the release of that force would give us nuclear power. Weak interactions is not so related to our daily life, but then it exists in beta decay, which of course we don't feel it every day, but this is essential. Without weak interactions, the world would not work. Yeah. So everything, all the other signs would not work. Despite that, we are not aware of them in every day. How it works can be viewed in a cartoon like this. So imagine that now there are two boats exchanging a ball, or 2 tennis players playing tennis. If when they were exchanging the tennis ball so fast, then to the outside world, it seems can view that the 2 tennis players are interacting. And you can imagine that if the tennis ball is heavy, then the interaction will be short-ranged. The 2 tennis players cannot be stepping too far apart, but if they are close enough, but if the tennis ball will be light, then they can be staying further apart and still interacting. So we have a similar picture, pictorial understanding of how elementary particles work. And to a physicist, all this, what I said in story form, cartoon form, can be expressed in mathematics. So which is called a standard model. And to a professional theoretical physicist of particle physics, he would describe what I said just now in a funny looking formulas like this. So today we absolutely do not need to get into this formula, but just to tell you that mathematics, formula is and the logical rules that comes with mathematics are the language of physics, language of science, from which we can derive things, predict things, and explain how the universe works. So we have the alphabet as in terms of quarks and leptons, and also the force carrier, but expressed in the mathematics in this form, and then some tools, and then we draw funny diagrams to turn these descriptions into diagrams like this to enhance our understanding of. So for instance, a Z particle would be interacting with this X particle would be coupled to a Z, and then Z would be coupled to something else. Then this is a physicist's way to describe how particle AN is interacting with particle B. So this is a broad sketch. Today we don't need to know about get into too much of the details. But this is how we understand the universe. Okay, now, so we understand a lot of the universe, but this is not enough. A lot to us is not a lot in absolute scale. It turns out that despite that we have great success in understanding the the matter, the alphabet, and the grammar that we are aware of every day. This muck, and then our computers, our lasers, and so on. So these are, but all this, protons and neutrons and electrons, make up only about few percent, 4-5% of the universe. And the remaining 95% is still not fully known. We have names for it. We know that there's a fundamental problems that we can account for all the energy density of the universe. We give them names: cold dark matter, dark energy, but we don't really understand what they are. Our standard model, the grammar and the alphabet I talk about, all those magnificent quarks, leptons, only constitute about a few percent, 4-5% of the universe. So there's a lot to do, a lot to understand. So somebody would call that the ultimate Copernicus principle, in which the stuff we know that we are not the center of the solar system, we are not the center of the universe, but now we realize that the stuff that make us up, that we are composed of, protons and neutrons and quarks and electrons, is only a minor fractions of the energy of the universe. So the bulk of the universe is still not fully understood, although we know that they exist. We need them to explain some of our data, which is not the theme for today, but in the future, some of the guests or myself, I can tell you more about that. Yeah. So now I talk about the standard model picture. There's a standard model of particle physics, but we also have a standard descriptions of the universe. The universe by now is 10 to the 10 years old, very old, a long time. But that long time to a physicist can be condensed into a poster like this, and in fact it can be condensed into a simple descriptions, and this is a simple description. The universe started off 10 to 10 years ago with a huge concentrations of energy density in an extremely small volume. We call it the Big Bang, and there's a big explosions, and then all the matter energy density starts to expand throughout, expands in the universe. So as you can imagine, at very high energy or high temperature, and when it expands, so what happens as time goes on? Energy is lowered, energy decreases, temperature drops. Well, this you don't need to be a physicist to understand that. I have a cup of hot coffee here. So as time goes on, this coffee would get cooled down. And then what happens when the temperature or the energy drops, temperature cools down? Then important things, structures form. At high energy, there tends to be less structures. At lower energy, lower temperature, structures tends to form. Also well understood, H2O, water vapor at high energy is a water vapor. When it cools down, then it becomes water. Water is more complicated than gas. And when it keeps cooler, it becomes ice. Ice is a very complicated object. There's a lot of crystalline structures. So structures form as the temperature lowers. So what happens in the universe? At first, it starts up as a very high temperature. A lot of elementary particles. All the alphabets exist in its free form. But then as time goes on, as it cools down, all those alphabet would find its friends and then start to couple together. A few quarks would gather together form a nucleons. Further cooler, and then several nucleons would gather together form a nucleus, and then further cooler, then the nucleon will capture an electron, becomes atoms, and then one atom becomes a multiple atoms, and very complicated atoms becomes organic molecules, becomes galaxies, stars, and eventually becomes ourselves. So we are part of the stories of cooling down. If there's no cooling, there's no complexity, and there's no culture, no civilization, no seminar as we have here. Only a soup of elementary particles. We have to thank to that to this expansion, to this cooling. Yeah, and then science also understand well where the understood part, the few percent of the universe, we understand it pretty well. For all the elementary particles, we have a subject of nucleosynthesis. We know where most of the atoms comes from. the very light atoms, helium and proton, comes directly from the Big Bang. So the hydrogen bottle, the helium bottle in your laboratory are remnant of the Big Bang. One can view it like this. Yeah. Whereas, and then but it gets, there are some lithium and so on will be produced at cosmic ray, and the intermediate mass atoms up to iron are produced in stars, like in the sun. Interior of the sun will produce other atoms, like including oxygen, carbon, that's the stuff that make us up. And then when supernova explosion would give the more heavier atoms beyond iron. So we also understand how these things comes from. Okay, now so in the last 5-10 minutes, I give a very broad view of how science, of an understanding of science, which is a cumulative knowledge and efforts for humanities it's not exaggerated to say that it's for the last 200 years. Now for the rest, we focus on one particular alphabet, one particular letter in this alphabet called neutrinos. Yeah. So neutrino history. Neutrino is a bit more than 100 years old, and we don't have to follow all the history, but it started off with an enormous beta decay, something that we don't fully understand in some data, and then Charwick, and then somebody would postulate that maybe this is a solution, and then somebody else, Ryans and Cohens, would really discover that, and then a bunch of other, and then following on, we try to understand it more deeper and deeper in more and more textures, more and more structures, more and more complications. We see those neutrinos from the stars, not just as an explanation of something far from the original goal of explaining something else. It has its own life in the stars and then sun, and we do experiments with it in various places. And so this would be the focus of today's story. Indeed, neutrinos is one of the 100 years old, 100 years of neutrinos. Neutrinos is one of the most favorite subjects of Nobel Prizes. So a lot of the grandmasters, you have, even for physics students, you have heard of Pauli, and then other recent scientists who do great contributions to neutrinos, and then we would come back to them as our story proceed today. So the story proceed in 100 years ago, more than in the late 19th centuries, the turn of the 20th century. People discovered that classical physics is not enough to explain everything. And in particular, atoms, at the lower level of atoms, smaller than atoms, there are a lot of things getting on. One of the things getting on is that there's some of the atoms, some of the matter is unstable. It can decay. One of the instability is to give beta decay, give out an electron. So an atom, bing, an electron giving out. This is called beta decay. So this we know from high school. Now, so beta decay is the emission of electrons. But scientists would not stop the knowledge here. They start asking the questions. What is the properties of this electron? It turns out it has charge, for instance. What is the energy of this electron? The momentum of this electrons. And it turns out that the momentum looks like this. It is a continuous distribution of momentums. Now, it's continuous distribution. So what is it? Then the problem comes. The most natural explanation at that time was that, well, atoms A decay into an electron and atoms B. This is a so-called two-body decay, A into electron plus B. If it would be the case, then we know about energy momentum conservations at school. Then the momentum or the kinetic energy of the electron should be monoenergetic, only one value, look like this. But it turns out to be continuous. It is a measurement, nothing. And then science, treasure measurement, data, very well. There's no use to say that, all the while say that it must be a two-body decay, it must be monoenergetic, full stop. No, we have to see it for real and to measure it and the measurement shows that it is a continuous distribution. Problem. So how come? And this is 1914, more than 100 years ago. Then 1930, an Austrian scientist working in Switzerland called Pauli would postulate that if this is no longer a two-body decay, it's a three-body decay. Atoms A decay into atoms B plus electron from something else. Then I can explain the three-body decay. Okay, so which by now we know that it's tritium decay into a helium, electrons, and antineutrinos. In this case, we can explain the three-body decay. Okay, but Pauli at that time is already a famous physicist. There's a Pauli exclusion principles among other things. So, but no matter how famous or how high-powered you are, we cannot take your words for granted. It's only at the end. You have to see it before it is established. So it is only 1930. It's only until 1956. Then the neutrino is finally discovered by two American scientists, Reines and Cohen, near a power reactor. And how they do it is a neutrino would by now they can starting off with various generations of physicists, including Fermi. Then science would expect that neutrinos would interact with the protons, giving neutrons, and then in electrons. So they have the electrons would give the positron would give us the pulse, and then the neutron would slow down after a while, and then gives us another burst of light. So they are trying to see in that detector. We don't have to worry about the details of the detector. Trying to see a two pulse, bing for the positron, and then waiting for a while, bing another bing for the neutron capture. So they are looking for bing bing in an environment, and they ask the questions: how many bing bing that we saw when the reactor is on, and then this bing bing when the reactor is off. And it turns out that there are more signals when the reactor is on, and the reactor is on. We know by that time what is a power reactor. How is reactor powered? Reactor is powered by fission, and in fission we produce two fission daughter, heavy atoms becoming into two light atoms. But those two light atoms are unstable. They will keep doing beta decay, on average 6 times to the ground state. So in a fission reactor, there's a lot of beta decay, and we know that beta decay gives you neutrinos. Pauli told us that. So the neutrinos, so reactor have neutrinos, and they saw something that is correlated with reactor on but not reactor off. Then this is a discovery of this is a data that supports the evidence of neutrinos. Neutrino really exists, and then we have some theory, some understanding of it. It's not just exists. We know that how it interacts with matters to a first level extent. Okay, so by now our roadmap of neutrino physics is the following. Remember that funny formula that I showed. That theoretical physicists say that they will understand the world. It describes the world with that formula. We don't have to ask for the formula, but among the formula, the several terms are related to whether they have neutrino mass. It's related to neutrinos. We want to see how those several terms are written. But in the laboratory, they manifest itself as properties, not as mathematical formulas. And the physical entities is neutrino mass. The neutrino may be massive, and this is UIG is neutrino mixing. We have 3 families of neutrinos. Those neutrinos can mix. And in real measurements, we don't measure mass, we don't measure mixing, we measure something else, some manifestations of mass, which is neutrino oscillations, neutrino interaction in terms of magnetic moments, or double beta decay, or the beta decay, how the spectrum looks like, and other things. So we do experiments in this arena. We try to understand neutrino mass and the mixing, and from this understanding, we try to construct a formula that describes the universe. This is our roadmap. But in order to do this, we need, and it turns out that neutrinos are subjects that, in order to do this well, scientists have to understand cosmology, astrophysics, nuclear physics, and particle physics. So see, this is a very rich subject. Sometimes in one conversation you have to discuss cosmology, but sometimes you have to understand how the nucleus works. And we have also used neutrinos as probe to understand other things. And it turns out that this mass is related to the structure and the composition of the universe, how the universe is made of, and also related to this Lagrangian, this term, which is the granular theories. So neutrinos is an object, in the universe that naturally connects the physics of the very big. There's nothing bigger than the universe, and the very small, how elementary particles work. So in one stroke of knowledge, we have to that it is connecting the biggest and the smallest entities of the universe. So that's why it is so interesting and important. Okay, now now we study neutrinos, but in order to study neutrinos, the first thing that we want to do is what? Is to see where the neutrinos are produced. So we know that neutrinos are produced in the reactor. This is the first sighting, but by now we know that neutrinos are produced in many things, from the sun, from the earth, from the reactor, from supernova, from the cosmic ray, which is now we call it atmospheric neutrinos, but it's cosmic rays, part of the cosmic ray neutrinos, and also from astrophysical objects. AGN is active galactic center. And by now we have good understanding that the universe, that in the room right here, there are various neutrinos coming through this room, and they are from various sources. Also from the cosmology, neutrinos are the neutrinos that is a remnant from the Big Bang, just like the hydrogen and helium in the early universe. From very low energy, note that this is the electron volt is an energy scale. This is milli and micro electron volt to PeV, 10 to the 15, 10 to 18 electron volt. Very low energy, very high energy. Out of this, the intermediate range, we have successfully observed them, but not the high energy one, the ultra high energy one. We are still, this is the future of science, which tries to observe the very high energy one, and also the very low energy one. So this is, and so by studying neutrinos from these various sources, we understand neutrino physics. And these sources are wild, which is natural, from the earth, from the sun, from supernova, and from the cosmic ray, or they are also be artificial. We can produce neutrinos ourselves, and the radioactive active sources in the power reactor. Power reactor is built by men, and then they also be produced neutrinos, and neutrinos also produced in various accelerators. In the accelerators, they produce neutrinos because they in fact in the pretty much the same mechanism as the atmosphere would produce neutrinos. And ultimately, in the composition of the universe, the neutrinos is around 0.5% of the mass of the universe is due to neutrinos, and comparable to the visible mass. Visible mass are stars, are the mass of the universe that gives light. That is around, which is the sun's. The sun is one of the visible mass, 0.5%, and then we have as much neutrinos in the universe as stars. So this is important. Although it is a minor fraction compared to other standard model particles, substance, free hydrogen and helium, or dark matter or dark energy. So these are the two parts, which is the dominant part, which we do not fully understand. Okay, now we have the neutrinos. We know where to produce them. We know where they're from. Now we have to study them. Now to study them, then we have to understand its interactions, the grammar. And it turns out that neutrino is only intact with weak interactions. Remember, there are 4 different interactions, and they are most substance would interact with all of them, but neutrino only interact with weakly as well as with gravity. How weak is weak? So this is the so-called cross sections, which is the probability of interactions of various things versus energy. So weak, strong means the y-axis here is in some unit called centimeters square, and this is called barns. Not very intuitive, but nevertheless, higher up, this is log scale. So higher up means it interacts more high probability, lower, less probability. So strong interaction is very favorable. Electroweak is less than strong, but nevertheless, it interacts with good probability. And the weak interaction neutrino interacting with matters is way down. So how way down is way down? So for instance, neutrinos has a couple of MeV energy, 2 MeV. The same as the Reines reaction. Reines uses to detect neutrinos, interacting on protons to give an electron to positron plus neutrons. When this neutrino from the power reactor, we have power reactor everywhere, so we know what it is. Now, if the power reactor has to go through water, so what do you think? How much water is necessary to stop this neutrino, this one neutrinos, on average? And it turns out that we need 250 light years of water to stop the neutrinos from the power plant. So this is called a lambda. It's called mean free path, which is how much materials is needed to, on average, to stop a particle, to interact with a particle. It turns out to be light years. So immediately, the consequence is that although the nuclear power plants produce a lot of neutrinos, we do not, and we cannot shield them. We just let it go out. There's no radiation problems with the neutrinos because it just goes through our body untouched. But then it also poses a problem. How can you study something that doesn't interact? When you have a friend that just walk around and do not talk with people, there's no way, this is little way to learn about, to know about more about your friends. You don't know what color he liked, what movie he liked, what songs he liked, what music he liked. No, because he walk around without talking with people. The only properties that we know about your friend is that he does not talk. He or she does not talk. So the challenge of neutrino experiments is how to beat this small cross-section. We have to study something sometimes called ghost particle, a very shy personality. Somebody said do not interact. How do we understand them? And the trick, maybe obvious in paper, is to build massive detectors. We need a lot of detectors. We really have light years of water, then we can study the neutrinos. Or we have a lot of neutrinos putting through a lot of water. But the challenge is that how to keep the cost and the background low. So this is far from being trivial. And that defines how neutrino physics is done. We have to be massive, but then it has to be relatively, the material cannot be very sophisticated, and also the background has to be low. And one of the tools to study neutrino physics is to do it in an underground laboratory. Apart from the reactor, of course, you have to do it at a reactor, but to study neutrino from the atmosphere, neutrino from the sun, we have to go underground. Why underground? Because the mountain, which is several kilometers of rock, would provide a natural shielding to the cosmic ray. So at least one component of the background is taken care of, cosmic ray. There's no cosmic ray. We will come back to cosmic ray later on. So this is one of the favorite place to do neutrino physics is an underground laboratory. Because neutrino doesn't interact, whereas photons, muons, electrons interact with much higher probability. We want to get rid of them. And a lot of them comes from the cosmic ray. In this room, where I'm sitting, and we are sitting now, 1 meter square of surface would have around 100 muons going through us per second. A lot. So we better get rid of them. And to get rid of them, we have to go underground so that the muons would be filtered off. Okay, now, so we have now the context. We know what the standard model is. We have given brief pictures of the standard model of cosmology, and we have given all the standard background history of neutrinos, where they are produced, how we do the experiment generically. Now we focus on one aspect of neutrino physics, neutrino oxidation, which has made important discoveries in the last 50 years. With this process, we understand much about neutrinos, mass, and then mixing. This is on our menu, on our theme of our roadmap. Okay, so, and then it is a saga. Saga is an epic, is a great story. So we listen to stories, and this story is not ended yet, but is one of the climaxes. Is of course, a few years ago, these two gentlemen get Nobel Prize for discovering neutrino oxidations in the various contexts which we'll come to. A Japanese physicist called Kajita and a Canadian scientist called McDonald. So the Japanese professor is part of the senior professor that built this big device called Supercamiocandi, and Dr. McDonald is the leader of this another device called the snow detector in Canada. So it's a Nobel Prize, but one would also emphasize that although by both for legality reasons and so on, Nobel Prize are only awarded at most 3 persons. But in this particular case, and in fact, in most cases in science now, it is not a recognition, not just a recognition of an individual, but then a recognition of a community of scientists, and also a recognition of a subject, which is to me more important. So it is a recognition that neutrino physics, in particular, neutrino oxidation, has made important advances that deserves a special recognition with this prize. And neutrino oxidation was discovered. These are the cartoon from the Nobel website. In a Supercamiocandi with the atmospheric neutrinos, in a snow detector with the solar neutrinos, and the Nobel Prize subjects results is shown here. Then we would get into this. These are the equipment. This is the result. This is the equipment. This is the result. Now we will explain this result, but here the result means that the data is different from the prediction, and here different data is consistent and is different from the prediction which is here. So prediction without oxidation, data. Prediction without oxidation, data. Then we get into the detailed story of this. The next level of details. First of all, solar neutrinos. The sun produces neutrinos. How is the sun powered? Now, if it is interactive, then I would ask the audience. But then now this is not visible, so I tell. So the lecturer have to tell the answer. Of course, the sun is powered by nuclear fusion. So the power from the sun is different from the power of the power reactor. So first of all, we have to understand. But both of them will produce neutrinos. So this is it. Although one is neutrino, anti-neutrinos, one is the neutrinos. Nuclear fusion is essentially protons after a series of nuclear reactions, which we don't have to worry about them today, into helium-4. 4 protons fuse together to form helium-4. And along the way, they don't do it in one step. They do it in an array of steps. Along the way, they will produce neutrinos. And among other people, a Grandmaster John Bacall, from a US scientist, have spent several decades calculating, predicting how the solar neutrino spectrum looks like. How many neutrinos would come from the sun, from our sun, and how the energy looks like. So, and this is how it looks like. This is MeV, because this is nuclear physics. Nuclear physics has to be MeV. And there's a most of the, it turns out that now this is log scale. So 99% of the neutrinos are low energy, around 300 keV. So-called the PP neutrinos. That gives us heat. So we know how hot the sun is. So we pretty much know how much neutrino is there. But for high energy, that is only a minor fractions, but still it exists. And then it is depending on the on the core temperature of the sun to not the spectrum, but the absolute amount of these neutrinos. Okay, now so there's a prediction, a theorist, and another US physicist since the 1960s in the mine, in the underground lab, which we mentioned in South Dakota, tries to measure, to find out the solar neutrinos. How he did that in a simple-minded language is that he has a big tank of fluid, detergents, and detergents has a lot of chlorine, and we know that if neutrino in there, chlorine will produce argon. So he would expose these detergents in the mine for a month, and then take it out, extract the argon, and then count how many argons are there that is correlated with the time being exposed. So idea is simple, and then we don't have to worry about that technique. But just to get impressed by the fact that after one, so there are 600 tons of materials here, 10 to the 30 chlorine atoms, and out of which there's around 10, 17 argon atoms after a month. 17 atoms. So scientists is able to manage to extract 17 atoms out of 10 to the 30 atoms. So this is a very impressive, cosmologically impressive numbers. So we don't worry about how Davis and his collaborators do that for today. But at the end, he measured that and find out that only he didn't get all the total neutrinos which John Bacall predict. It's only 1/3. So since the 1960s, 50 years ago, it is called a solar neutrino anomaly, becomes a problem. But finally, it becomes a Nobel Prize for Davis for discovering that. But before the confirmations, they only see one number is less than the other by a factor of 3. It can be an experimental problem. He may not understand his experiment. It may be the model. The theorists may have calculated something wrong, predict something wrong. Maybe they have used a wrong parameters. Remember that I mentioned that these numbers, the prediction, depends critically on the temperature of the sun. How do we know the temperature of the sun so precisely? And then it may be due to neutrino problems, which is the most interesting scenario, and something we don't understand. And history tells us that eventually the answer is this. But it was by no means obvious that it has to be like this in the 1960s. But still, in 1960s already, theorists already speculate that if Davis' experiment is really due to neutrino properties, then a natural explanation would be that this is neutrino oscillations, that neutrino from one flavor would turn into another flavor on its way from the sun to us. We know that neutrino, at that time, there's already 2 neutrino flavors being discovered, so this is very natural. And we know that the neutrino produced from the sun is from one flavor, electron neutrinos. So if it goes into other flavor, neutrino mu, then of course the detector only detect electron neutrinos, and of course it gets less neutrinos detected. So already Pontic-Cobo and Gribov in the 60s already pinpoint an explanation. But of course there's no proof at that time. Not even the data is not, whether it's a neutrino is not confirmed, but at least, the theorists already have an idea that this can be related to neutrino oscillations and therefore neutrino mass. But being fast forward for 40 years, by 2000s, there are several experiments that show similar things as Davis. A gallium experiment, similar radiochemical experiments, the water experiment and heavy water experiments, all seeing less neutrinos when they're only sensitive to electron neutrinos. So not just one experiment, but 4. So now it's getting so-called, the plot gets thickened. So it is more and more, it is unlikely that Mr. Davis make an experimental mistakes. But this is still not a proof that neutrinos is the explanation. It can still be the theory. We don't understand the sun interior temperature extremely well, too well. Okay, and among this is one technique which is called Chirenkov radiations. Chirenkov radiation is that when a charged particles would move in a medium faster than light in that medium, there would be a cone of light coming out, and that cone of light, the angle would be characteristic of the velocity, the momentum of that particles, and how much light can tell us what is its energy, and also the direction defines the cone directions. How the cone looks like will tell us what is the direction. So indeed, then physicists make use of these mechanisms to detect neutrinos. And one of the big detectors is in Japan called Supercamiocandi. This is a very interesting scenario. In Japan, again, in the middle of a mountain, 1.5 kilometers in depth, is this Supercamiocandi detector made up of 50,000 tons of water in the middle of the mountain building, surrounded by more than 10,000 of photomultiplied tube, each with 50 centimeters. It's a photomultiplied tube with 50 centimeters, which is 50 centimeters is that big. So this is 1 meter, so this is 50 centimeters. So it is a very, very, very sensational sight if you would sit in this place. And indeed, these are the Japanese. This is the physicists surfacing the detector on a raft and then putting in cables and then cleaning the detector and so on. So this work can also be very exhaustive, but also very fun, very exotic. Now, with this detector and with the Chirenkov technique, which I mentioned in 2 transparencies ago, this experiment can see neutrino from the sun. How does it work? So neutrinos coming from the sun. Remember that they produce Chirenkov cone, and the cone tells you the direction. So they measure both the energy as well as the direction of the neutrinos. And indeed, there's an enhancement of neutrinos facing the sun. At any given time, we know where the sun is. So it's always from neutrinos, there are more neutrinos coming from that direction, and that direction is the direction of the sun. So therefore, this is a proof that they really see neutrinos. So what the experiment does is they measure the excess of red, and anything else is background, and then compare with the expectations. And indeed, again, they said less neutrinos than expected. And what is interesting is that seeing neutrino from the sun, from the interior of the sun, is a proof that the sun is working. Present continuous tense. The sun is burning. When we go out, this is hot summer. When I go out from my building and see the sun and feel the warmth, it is not a proof that the sun is working, because the heat coming to us is from a nuclear reactions millions of years ago in the interior of the sun. Seeing the sun now is only a proof that the sun was working millions of years ago. But seeing neutrino is a proof that the sun was working at least 8 minutes ago. So this is some philosophically, this is a very interesting scenario that the physicists working in the interior of a mind never see the sun, can understand, can probe directly the interior of the sun. So this is the amazing things about science. And also, when they ask the questions about this red area as a function of time over the year, they saw some variations. Why is the amount of neutrinos changes over the year? Because the Earth to Sun distance is different. The Sun works. The Earth circulates in the elliptical orbits in the Sun, and the winter summer distance are different. And so this is a measurement of the eccentricity of the Earth's orbit. This is not a circular orbit, it's the eccentricity of the Earth's orbit. Again, a very interesting scenarios that eventually leads to a Nobel Prize for this Japanese physicist. Okay, I also mentioned another player, the gallium experiment. Also, radiochemical experiments measure the pp neutrinos, the 99% of the neutrinos. Again, they saw 30 atoms, out of 10 to the 29 atoms. So this is but we know how hot the sun is. We know how many neutrinos are without relying on theory too much, because we know the heat of the sun, and so we know how many pp neutrinos is, and then it doesn't match. So this is one of the experiments that shows that that turns the tide, that although we don't fully understand why, but it turns out that neutrino physics is a more and more likely problem of the solar neutrino puzzle. We see less neutrinos because we do not understand neutrinos, not because we don't understand experiments. We do not understand the sun. So this is an experiment that changed the tide, telling people that there's something wrong with the neutrino physics. But eventually, it is Snow, this experiment, that really put the coffin nail. Snow is an experiment in Canada, again, in a mine, under 2 kilometers of rock in a mine. So what is this? Is basically a big balloon of heavy water surrounded by ordinary water, and then surrounded by photomultipliers too. So that's it. So this is what the snow detector is, sitting in a mine. So why heavy water? The heavy water is the key. Heavy water. What is heavy water? Heavy water is, instead of proton, it is deuteron. D2O is heavy water. Okay, so it turns out that this object, deuteron, can have a diverse and have more interaction with the sun. So this is so-called electron scattering, charge current, and neutral current. So this happens for electron neutrino only. This happens for all neutrinos, but favored with electron neutrinos. And this is democratic. All neutrinos can interact with the so-called neutral current. So it's like seeing things with 3 eyes. By seeing the same thing, solar neutrinos with 3 eyes, then you've got different sensitivity. Our eyes, we saw 3-dimensional objects, the stereo information, because we have 2 eyes. And Snow experiments, seeing things in 3 different directions, can have a lot of resolving powers to understand the problem. And this is the Nobel Prize results. So it turns out that, remember, that they are seeing things in 3 different ways: the blue way, the red way, and the green way. Traditionally, in the past, whereas the dotted line is the prediction of standard solar model following Becquerel. The axis this is the electron neutrino, this is the other neutrinos, muon, tau neutrinos. Electron neutrino is produced from the sun. So if we only see electron neutrinos, then the prediction is this dotted line down to the edge. It will be here, but the experiments here. So this is a solar neutrino problem. Prediction here, measurement here. The prediction is go all the way is here. This is less than this, solar neutrino problem. But it turns out that the missing neutrinos are the neutrinos from the mu and tau that can interact with the blue way, and in particular the green way. So there is some neutrinos that is not electron neutrinos, but then turns into muon and tau neutrinos, but they're still intact. And there is a consistently intact here, which is consistent with the standard solar model. So this is the amount of the total flux remains the same. So this is a very convincing proof that electron neutrinos coming from the sun is converted to other neutrinos on its way from the sun to the earth. And those other neutrinos is detected by this experiment, and the sum adds up to be the solar model predictions. So the problem is solved. The solar neutrino problem is solved, and this experiment would get Nobel Prize. So, and it would be the textbook story for our future textbooks, for our children and grandchildren ever after. Okay, so neutrino from the atmosphere. How the atmosphere will produce neutrinos? Cosmic ray is not from the cosmic rays on Earth. It's not from the cosmos. It's from the atmosphere. therefore atmospheric neutrinos. What happens is that some heavy ion, in particular helium, proton, high energy, would come from the cosmos, hitting the upper atmosphere of the Earth, and then a lot of the interactions happens. But most of the interactions are short-lived. Pion, muons are short-lived. They would eventually decay into being neutrinos, and the neutrinos would come, and the neutrinos would just come through Earth. So if we have a detector here, they will see neutrinos here from this side, also from this side, from everywhere. And the angle will corresponds to what? Measurement of the angle is a measurement of distance. So although we in the detector we measure angle, but the angle tells us how long that neutrino has traveled. So this is the brilliant concept of this concept of this experiment. Okay, so it started off with early experiments studying for proton decay in the 1970s. But the proton decays had two experiments, IMB and Kamioka, the predecessor of Supercamiocandi. They don't see proton decay. At that time, atmospheric neutrinos are called irreducible background. But the physicists study this background in detail and find out that there are more informations. They make a discovery that this is not as we understand. There are new understanding to it, and that becomes a signal. Whereas proton decay is never seen. Both detectors also observed supernova neutrinos in 1987. So what happens is that, so in the 1980s, 88, the first experiment, Kamioka, already see some hints that when the angle is big, that means the neutrinos come from the other side of the Earth, suggests that the neutrinos go for long distance. They are not seeing as many neutrinos as they wish, as a standard model. This one means muon to electron neutrinos versus signal versus expectations. And if everything is right, and nothing happens, then it's just one. But we are seeing less muon neutrinos than when the neutrinos comes down from the top, from the bottom. 1980s. This is already a suggestion, but it's until Supercamiocandi comes along. Now I mentioned about this, and at that time the leader is this man called Tsuzuka. And then this experiment will see Chirenkov detector. So we mentioned the concept, but this is the real data. If it is electron, it looks like this. A muon looks like this, and then a 2 gamma looks like this. So by eye, you can tell this is different from this, This is cleaner. This is a bit more fuzzy. This is even fuzzier. So the position of the end of the circle tells us where the neutrino comes from, the direction, and therefore the distance, and also the amount of light tells me what is the energy of that neutrinos. Okay, and then in words, it is that you look for this event many times, do all the accounting, count your fingers, and then you get the result. And this is the result as presented then, which is the Nobel Prize. We don't have to worry about the too many details, but the main details is that if there's no oscillation, it would be the red curve. If there's oscillation, but the data suggests this. It's always that the downward going muon neutrino have no problem, consistent with models, consistent with no oscillation. But then the upward going neutrino have problems, have a deficit, no matter where you look for it. Yeah. So these are different energy and then different textures and different topology. We don't have to worry about that here. No matter what, it never fits the red line, and it never fits the red line when this is upward going. Although the downward going part is okay. So this is another way to say that neutrinos, muon neutrinos, is converted into other things. Electron neutrinos, and it travels long distance. Short distance, it won't change its identity, but for long distance, it would change its identity. Another smoking gun of neutrino oscillations. okay, which is Nobel Prize. So now we measure neutrinos from the wild. That gives us a lot of information, but we also do neutrinos from the accelerator. Now, accelerator is we build accelerators, and then we build detectors, and then electron, photons, muons, and so on have different topologies in the detector, and so we can control the energy and then control what is the flavor, knowing event by event what sort of neutrino it is, and what sort of signatures by measuring knowing that it is electron, muons, and so on. Yeah, and out of those experiments, several earlier generation of experiments. So from there, Fermi Lab to in the U.S. to Minnesota, at CERN to the Gran Sasso Laboratory in Italy, and also in Japan, from both the KEK laboratory shooting neutrino beam to Kamioka, the Supercamiocandi detector, or from the Tokai now to the Kamioka detector. This is 700 kilometers, around 300 kilometers from here to here. So neutrino is produced at the accelerator. It goes through hundreds of kilometers to the detector. We try to ask the question, does it disappear? And indeed, it disappears. Again, we do not go into details, except that, for instance, the K2AK experiments, when all the muon neutrino produced at KEK would survive on its way to Kamioka, it would look like this, but the experiment measured this. So again, neutrino disappears, neutrino oscillates away to other. And also, well, here, because it has more control on the energy, so we can see that the disappearance, the deficit, has some functional form. It depends on energy. So now it's getting more and more. This is how science works. We learn more and more. We don't only just say neutrino disappears, but then we ask the question, what is it dependence? Now we know that it depends on the length, on the distance. Now we know that it depends also on the energy. Different energy have a different disappearance probability. Now we start to understand more and more. And with more data, it becomes like this. This is the Minos experiment. Again, the same philosophy. We need it to disappear, and the disappearance depends on how much it disappears, depends on the energy. Also, at the reactor, at the same site, Kamioka mine, another Japanese experiment called CAMLAN would be a big liquid scintillator detector, 1 kiloton, 1,000 ton of liquid scintillator, organic substance, a lot of C, but a lot of H. And then it measures, and then it asks the questions, what is the neutrino energy measured? And indeed, it is measuring less neutrinos than expected. Neutrinos that comes from the various reactors in Japan, going through hundreds of kilometers to the Kamioka, CAMLAN detector. Some of them is turned into something else, no longer electron antineutrinos, and it depends on energy. The deficit depends on energy. The same experiments, CAMLAN would also be the first to measure neutrinos from the Earth. After all, the Earth has a lot of uranium, thorium. The Earth crust is powered by radioactivity, and radioactivity has a lot of beta decay. Again, beta decay comes back. Beta decay gives out a lot of neutrinos, and this neutrinos is successfully seen by this CAMLAN experiment because it's sensitive to electron antineutrinos, sensitive to the decays of beta decays. Product. The Earth, radiogenic power. The Earth is powered by radioactivity. In the 19th century, one of the big problems is that why in underground it is not getting cold. Even in the tunnel, it is still warm. Something is powering in the ground, and then it is isothermal. Everywhere it is similar temperature. So now we know that it is due to radioactivity. And beyond the reactor, the new experiments in China called Taipei, in Korea called Reno, and in Europe called double shows, all see another mode of neutrinos. So they have a different distance as CAMLAN, 1-2 kilometers, and they saw a neutrino deficit, smaller deficit, but nevertheless important, and they see the third neutrino oxidation channels. Remember that there are 3 families, and there are 3 neutrinos, so there would be 3 different ways to oxidate for it to move. In a 3x3 matrix, there would be 3 angles to parameterize that. So within 10-15 years, we saw all the 3 angles, all the 3 channels, and this is the last one. It's called theta 1,3, and this as compared to theta 1,2 and theta 2,3. There's 3 angles, and the reactor experiments see this remaining angles. We don't have to worry about all the details, but then it's more important to know about the story. Yeah. Okay. So this is the deficit. Now we put everything into perspective, how things evolve. So neutrinos there. This is neutrino. Now we saw a lot of data, but we have to understand what the data works. And up to now, our understanding is in words. Neutrino oscillations. It changed from one family to the other. But physicists are not satisfied with this description. We have to turn it into mass, into a very vigorous language, and mass is a vigorous language. So there are 3 families of neutrinos. So the 3 families will be correlated to the so-called mass eigenstate. Neutrino different mass they will mix together to form each of this flavor through a matrix, which is 3x3. A 2x2 form would be like this, which you may be familiar with in your math lessons. But this is one application of the mixing. So neutrino mass would have a special form state called certain mass of 1, 2, and 3 have a definite mass, but when it interacts as like an electron neutrino. It is a mixture of 1, 2, and 3 at different proportions, and this description is the optimal way to describe this 1, 2, 3 mixing differently is with matrix, a 3x3 matrix, and with a 3x3 matrix, and with these descriptions, then we got various formulas which we don't have to worry about that. In the 2x2, if it is 2x2. We saw that the neutrino oscillations would depends on delta m squared is related to neutrino physics, nothing we can control. This is what we want to find out. But now we know that it depends on distance, it depends on energy. This is something that experimenters can tune. We have the knobs that we can turn. This is the things that we can control, we can measure, L and E. And with L and E, we know the delta m squared, which is the difference of the neutrino mass from the 2 so-called eigenstates. From the 2 state 1 and 2, then there's a delta m squared 1 and 2. And from this, we understand about neutrino physics at a more theoretical level. This is the theory of neutrino oscillations. We don't have to get into this, but then just to give a flavor. And there are complications when these schemes will work in matter. For instance, when neutrinos go through the sun is not a vacuum. And because in the vacuum, there are more electrons with no muons and tau. Then with some very tricky mathematics, then there can be an enhancement of the process, amplification of the process called matter effect, so-called resonance. We don't have to worry about that, but then this is a very interesting subject. So theorists work out the theory to interpret the data. So where are we? 20 years ago, I mentioned that now. So the delta M squared is one parameter. Another parameter is theta, which characterize the neutrino mixing. So we want to change L and E to find out delta M squared and theta. So 20 years ago, on the log plot in delta M squared and theta, there are various allowed region. As time goes on, with atmospheric neutrinos, solar neutrinos, this allowed region would be collapsed into smaller and smaller. So at first, we don't know where the effect is. This is somewhere here, but we don't know where. And there will be three effects because there are three angles. With a definite experiments, it pinpoint the effect into a smaller and smaller region. And then with the Camlan, with the various accelerator and Camlan experiments, it is confined into a smaller and smaller region. So the thing to look at is that when you get to smaller and smaller region, this is becoming more and more well defined. This is almost when they plot like this, when this plots with this goes with this, it becomes a linear scale. We start off as a log scale, and then to a linear scale to understand our physics. We're getting things more and more precise. We need numbers. In science, it's just saying that there's neutrino mixing is enough, neutrino mass is enough. We want to measure the mixing, we want to measure the mass as accurate as our technique can allow. That means that when we don't know things, when we don't know where to look for things, we present our results in log scale. But when we understand things, we present our results in linear scale. So this is a sign of improvement of our understanding of our language, and eventually this is more and more the converging answer. We don't even present things in figures anymore. Even in linear scale, we present it as a number with error bar. So that means a more and more advanced understanding. And we also see oscillation means that oscillates means it can go up, it can go down, it can also go up. And both Camlan and Supercamiocandi experiments successfully see this turnover, how it changes with L over E. So the thing parameter we control is distance as well as energy, and there's a certain relationship. It is not flat. So this is also a bulletproof proof that neutrino not just disappear, but neutrino oscillates is the correct explanations of what we have seen. Okay, so by 2015, there are three channels, and the three channels and the three results are here: small one, and small one. In this sea of log plot, a few small dots is our results. This is what science would hand down to future generations, and then this would be in textbook. So what have we learned? Although the Nobel Prize is given to two physicists, but from this, one would conclude that there's a lot of people have contributed to make this plot. A lot of people, not two individuals, although the contributions is tremendous. And now we can infer that science make progresses by dispatching 1,001 competent teams to look for new things, knowing that the odds of success is only 0.1% in each. So this is a big C. So we are sending now, just to illustrate a point, 1,001 team to look for things everywhere. Each of them has only 0.1% chance of success. But on average, somebody would succeed and then find that pot of gold. In a sense, this is how science and how civilization make progress in our area. Okay, which is symbolized, which is presented in a diagram like this. So we see this grandmaster making mistakes and then crossing it out, saying that he himself, telling himself that he's wrong, and eventually he get the correct answers. So the important thing is not just the correct answer, it's also the mistake. Somebody will look for the wrong area, and then somebody will show that they are wrong, and then so that we can converge, everybody can converge in the correct answers. Okay, so now to put it into broader into broader perspectives. So I recall that, right? At first we plot exclusion plots, and then we plot allow region, and then eventually it becomes a bunch of numbers. So the steps are, first of all, we confirm incomplete understanding. We have, remember in earlier we have the data. David's data doesn't agree with the solar model, but there are other reasons, not just neutrinos. A lot of the times, most of the discrepancies are due to other things, not fundamental. Only in this occasion, this is fundamental. So when it's fundamental, then this is already a big understanding that this is a fundamental problem. Then we identify crucial parameters. In this case, delta m square and theta. Difference in mass as well as mixing, not other things. Then we plot exclusion plot in log scale, allow region in log scale, measure region in linear scale, and eventually it becomes numbers, XX plus YY. So this is the progress of science from enormous data to a real understanding, real precision measurement. And in terms of theory, we have some. We can construct our 3x3 matrix, and then we understand this delta m square. We understand the theta, but there are still some missing. And then we'll tell you this understanding. We have gone through a lot. We understand a lot of things, but there are still some missing link. The missing link now we understand. We know that neutrino oscillates, and then we know that this delta m square is non-zero, but we do not know whether the three neutrino masses eigenstate are structured like this, which is called the normal hierarchy, or the inverted hierarchy. We don't know. The data is consistent with both. And we do not know where the zero is. Whether the zero is here or way down, we don't know. We don't know where the zero is. We only measure the difference of neutrino mass. So these are one of two main problems. We know the absolute scale. We don't know the hierarchy. And so this is another way of showing our understanding. We know the angle of, we know the mixing matrices, and then in terms of numbers, but we do not know whether this so-called the CP parameters, whether neutrino and anti-neutrino have the same oscillations. We don't know the structure, and we do not know whether this so-called phase, whether so-called a CP charge and parity in our language, whether neutrino and anti-neutrinos have the same oscillation parameters. But to understand further, there were new projects in Japan. There's a new running experiments from Tokai to Kamioka, and in the States there's a Fermilab to Nova experiment. Both are running projects. And in constructions, there's in the US there's a Fermilab to the South Dakota Stanford laboratory, thousands of kilometers, and also in Japan to Kamioka with the Hyper-K experiment. This is a doing experiment and the Hyper-K experiments. We don't have to worry about the details of that, but these experiments together with the running experiments now T2K and Nova, but tries to resolve the questions about hierarchy as well as whether there's a delta CP, whether there are CP violations in the neutrino, so-called the leptonic sector, whether the matter and antimatter would behave the same. Well, stay tuned, and then we may have more to come in the coming decade. What does it mean? It means that we know neutrino oscillation, but the story hasn't completed yet. There are some residual holes to fill in before we claim fully that we know how to write that mixing matrix in the formula, in the standard model formula that we showed early on. Right now, we know the form, the direction is right, but there are still a few symbols that has to remain symbols. We want to put numbers to it in that formula. And beyond oscillations, there are other walks of neutrino experiments. There are neutrino experiments to look for neutrino projects, to look for supernova, to study supernova, to study the cosmology, to study double beta decay, and to study again our good old friend beta decay, measure the beta spectrum. Among which the measurement of beta spectrum is getting more and more exquisite. Remember that 100 years ago, this is continuous. Now it is still continuous, but it is measuring more and more precisely. And the idea is to measure the endpoint, the smallest part, more and more precisely. And the shape over there will tell us what is the neutrino mass, that absolute value of the neutrino mass. And in order to do these small values, you need a very big detector like this cat-string experiments in Germany. So this is a very nice pictures of how big the detector is to go through the small villages in Germany. By now it is probing around 1 electron volt, but still it's not a positive measurement of the neutrino mass, and we don't have to worry about how the principle of the experiment, except that it is very exquisite, and to do this is requires several decades of work and development. In double beta decay is a project that will try to ask the question: is neutrino its own antiparticles? Is neutrino and antineutrino the same particle, only reversing a spin? And in order to study this, the physicists try to look for neutrinoless double beta decay. In certain elements in nature, it can emit not just one neutrino, but emits two neutrinos. And when those two neutrinos, emits two electrons. When the two electrons would come now without neutrinos, then the two electrons would have a monoenergetic, a peak structures. And these peak structures would exist only if neutrino and antineutrinos is the same particle, a so-called Majorana particle. If neutrino is a Majorana particles, then this, in this case, molybdenum, but it's also for xenon and also for germanium, can have a structure like this, so-called neutrinoless, no neutrino, double beta decay, emission of two electrons. This is a big project. This is not being observed yet, but there's an intense activities worldwide to look for it. And we also use the neutrinos to study the sky. We study neutrinos from the astrophysical objects. In astronomy, scientists have studied gamma rays in many different wavelengths, electromagnetic wavelengths, and but because if they are gamma rays, then there should be some hadronic components from pions, and then pion would decay to neutrinos. So one should expect neutrinos as well. And in order to do that, scientists have built big detectors. Again, we need big detectors in different places in the ocean. And in this example, in the South Pole, in a big sheet of ice. So in words, in simple terms, what does it mean? It means that in the, this is first of all the geographical South Pole. South Pole is here. Everywhere is facing north at this point. So the idea is to drill holes several kilometers deep, put in a strings of photomultipliers tube there, let it frozen, and see whether there's light. And then indeed there are some light, and from the light one can infer that. So this is the South Pole, and then when a neutrino come, high energy neutrino produce a muon. Muon goes through, there will be a bunch of light that can be as strong as this. And indeed, this experiment, ice cube physicists would measure the energy spectrum of this light. There are different ways. We don't have to get into details. And it is more than the atmospheric neutrinos would give, expressed at the high energy, 10 to the 6 electron volt. Remember that 10 to the 6 giga electron volt, 10 to the 15 electron volt. Remember that reactor solar neutrino is around 10 to the 6 mega electron volt. Accelerator neutrino is around 10 to the GeV, 10 to the 9 electron volt. This one is 10 to the 15 electron volt. Very high energy. Less in neutrino flux, but when it interacts, it can be very spectacular. Indeed, they have this experiment have confirmed that they are astrophysical neutrinos, which is like this. And towards the future, a big movement in science is to do so-called multi-messengers astronomy, to reobserve an object, not just with gamma ray, X-ray, but now also with cosmic ray, and also with neutrinos, and also with gravitational waves. When we will study the same object, remember, we want to do it in many different angles. We learn more about that object and about the physics of that object. This is the direction of astronomy in this centuries. Studying objects with many different wavelengths, as well as different scenarios, neutrinos, as well as gravitational waves. In this respect, we have already seen a very spectacular neutrinos in 1987 from the supernova at that time. So the Kamioka, IMB, as well as the Baksan experiment have successfully at the same time see pulses from the supernova neutrinos. And this already confirms that, tells us a lot about neutrino properties. And in the next supernova, then we will learn more about the neutrino properties, as well as the supernova physics, internal structures, when the next supernova comes. And the various big detectors, including the Supercamiocandi experiments, which we mentioned, are watchful, can be active when the next supernova comes, and then seeing many more events, seeing really how the different flavors of neutrinos evolve, combining all the detectors together. Another thing to look forward to in any time. We cannot control when the next supernova comes. And we recall that also neutrinos is also related to cosmology. The cosmology, it tells us about cosmic neutrino abundance, how many neutrinos are there, and how many neutrino flavors are there. It tells us about what is the neutrino mass, and also both neutrino flavor as well as neutrino mass. Neutrino abundance can be inferred from so-called Big Bang nucleosynthesis. Early on in the Big Bangs, the light elements start to form: helium-4, deuterium, helium-3, lithium. And when we measure the abundance of those primordial of those, it tells us much about the physics at that time. And it turns out that the fine details of those physics will depend on how many neutrinos are there. And we know standard model tells us about 3 neutrinos, but if there are more neutrinos, these numbers would be would be different. For instance, the helium-4 abundance would be different. 4 neutrinos would have a slightly higher abundance for helium-4. Astronomers go out, measures how many helium-4 are there, and then infers that there are indeed 3 neutrinos. So this is already a triumph in science, that we measure the early universe. Helium-4 can tell us about in the universe there are only 3 types of standard model neutrinos. Not just that, and then astronomers also measure the relic photons of the sky, which is called the cosmic microwave background. Different generations, you can appreciate without knowing the details, the progress. 20 years ago, 30 years ago, the resolution is like this. 20 years ago is like this. 10 years ago is like this. More and more fine, the same sky, more and more fine structures, more and more better resolutions. And indeed, by studying the so-called power spectrum, the distribution of this ups and down fluctuations can tell us much about how much matters are there in the universe, and then how much dark matters and how much photons and so on, including how many neutrinos are there. Indeed, it is consistent with that there's a 3 active neutrinos. By studying, again, now this is a cosmic ray microwave background. Another triumph of science that we look out for the sky, look at the fluctuations of the photon spectrum, can tell us about how much mass are there in the universe, how many neutrinos are there in the universe. And also that is photons, but the universe also consists of matters. By studying how the matters are distributed, we can tell about what the neutrino mass is. For instance, this is in blue and in red. One of them is simulations, and one of them is observations. This is how the structures of the universe, how the mass are distributed in the universe, and the simulation is based on the fact that neutrinos are very light and there is dark matters. If dark matter is made up of neutrinos, of light neutrinos, the universe will look like this. Certainly very different from here. From this, one can exclude that the neutrinos cannot be the dark matter of the universe. Dark matter has to be something else which is slower, colder. And by studying the fine details, one may be able to measure the neutrino, the fine distributions of this spectrum. One may be able to measure the neutrino mass eventually from cosmology. Okay, so now I'm about to conclude. I hope that I give you a big tour of basic science and a little bit of cosmology, in particular the story of neutrino oxidation. So there are fundamental conflicts right now. The future, we're talking about the future. What to expect for you if you want to learn more about science, and these are things to expect. There are fundamental conflicts between the universe when we try to understand the universe through gravitation or through particle physics. Gravitation with general relativity, particle physics with standard model. The experimental data and the theoretical formulation doesn't match. Experimental data tells us that when we start to understand it with gravity or with light, there are differences telling us that dark matters or dark energy. So in the terms of theory, there's still no quantum theory of gravity. It looks like that daddy and mommy doesn't talk to each other. They are using different language. This is very strange. So we find it's a problem. We think that right now the data, this conflict seems to can be resolved by having 95% of the energy density of the universe is understood, dark matter and dark energy. So there must be some new physics there, and we want to understand what the new physics is. We want to understand what antimatter. The universe is made of, observed universe is made of matter, but not antimatter. We do not say anti-star, anti-galaxy. But in the beginning, matter and antimatters are produced symmetrically. So where have they disappeared? Why do they disappear? So why is it totally absent? Why is it although why is the antimatter absent? This is a big problem. How to describe the early universe is a big problem. And also there are problems of discussing that what happens before the Big Bang. Can it be studied by science itself? Because there's nothing to observe. So how can we do science? Although important as it is, are we able to do any science investigations to ask the questions before what happens before the Big Bang? But at the end, we should have confidence in the power of scientific investigations and the powers of scientific investigators. More than 2,000 years ago, we started with the ancient Greeks. Ancient Greeks starts to understand they have a dark matter problems, and they do an experiment like this. This is the discovery of air. That there is something between you and me, and this is called air. And they have models. Air, fire, earth, and water would constitute the universe. These are wrong, but they set the stage of subsequent investigations. And in a sense that the outcome of this, the solution of this, is the periodic table. We understand the matters up to the level that we can touch. And then 100 years ago, the Europeans, starting from Europe, they find out that subatomic matters decays, and eventually becomes the standard model of particle physics after a whole century. And today we tell the stories that we start off with a continuous beta spectrum, and with Pauli predicting that the neutrino is a solution, and now we get to the stage of discovering neutrino of mass. They are mixing and can pinpoint that the structures can be like that, but there are still residual problems to study, including whether it is this hierarchy or that hierarchy, what is the zero, and whether neutrino and anti-neutrino are the same object, or do they, or and so on. Okay, so the powerful play goes on, and then there are a lot to do in putting the dark matter. These are the two early pioneers of dark matter, and then we have the dark matter problem, and then hopefully, we don't know when, but hopefully not too soon, and then still within our next decades and so on, within our lifetime, we will have find solutions, and then finish the same story as we did successfully with our other stuff, and solve the dark matter, dark energy issues. Okay, so finally, neutrinos are important but strange objects from today. History of neutrino physics is full of surprises. I hope that you would appreciate not just the science. You come home saying that neutrino have mass. This is not most important. It's that the history, the story behind how science works. To me, it's more fascinating. The saga of massive neutrino and finite mixing is the theme of today's talk. From this, we learn that there are physics beyond the standard model. We review their double experiments and projects coming up, even more excitement. And neutrino may also be the avenue to the dark matter problems, both in physics-wise and also from experimental techniques. Okay, so my little lectures ends here. So this is not for that they will not turn you into experts, but hope that it would give you a general knowledge, as well as inspiring some of your interests, as well as some motivations to learn more in the future. And good luck in your studies. We can entertain some questions now. Thank you.
Yeah, thank you, sir, for your wonderful presentation. You have talked a lot of things about neutrino physics and their detection and other things. So I think students have learned a lot of things. So we have got some questions. So if you allow us, so we can start our discussion.
Yes, please,
sir.
please.
So the first question: what do you mean by cool down? Where does the everything go after Big Bang?
Where does everything cool down? So the Big Bang starts off with very high energy density in a very small volume. So this very high density, so this extremely hot. Hot is our language, but it means that the kinetic energy is extremely hot, extremely high. But as the space-time expands, then it's just like a balloon expanding. So it would have less and less energy. We use the word like as a temperature. There's no such thing. Temperature is a macroscopic description, but it is actually the energy, the kinetic energy of the things that are produced in the Big Bang becoming less and less. The elementary particle is produced at very high energy, but it becomes less and less. So globally, macroscopically, we call it cool down. We put a temperature to describe that, but eventually it is that because of the expansions, just like the expansion of a balloon, the kinetic energy becomes less. So we use the word cool down. Temperature becomes less, and when this is getting temperature become lower and lower, the structure becomes to form. Those elementary particles are no longer free. Those electrons are no longer free. They would couple to an atom, to a nucleus to form an atoms, and so on. So this is a description of what is happening. If this is the question, this is the cool down. Yeah.
Thank you, sir. So we have a question. So where does the most energy of a particle produced in accelerator come from in high energy physics?
The highest energy is in the CERN accelerator at LHC. So they are producing TeV-ish energy. TeV is a 10 to the 12 eV. Yeah, is around that scale. But remember that when I talk about so human accelerator at CERN, a very big project, they have discovered the Higgs at 125 GeV out of a multi-TeV beam hitting together. So this is already tremendous in human technology. But the cosmos, I show the ice cube events. They can be as high as 10 to the 15, 16 EV compared to 10 to the 9. So there's another million times higher energy given to us by at least by the astrophysical objects, and we have seen them. And we would like to see even higher energy cosmic ray. Yeah, in fact, cosmic ray has been seen to even higher energy, 10 to the 19 EV. Yeah, so the mysterious of the cosmos. They have some big engines to supernovas, and then some many very violent phenomena that gives very high energy events.
So thank you, sir. We have another question. Is the neutrinos rest mass is reality or is
so
an
say
illusion?
it again. I don't fully catch.
So is the neutrinos rest mass is reality or
is the
illusion?
now? So let me understand. The question is the neutrino rest mass?
Yeah. Okay, I can add the question in the screen. You can see.
Okay, well, now the science will try to describe reality. We have seen neutrino, so neutrino is a reality, but we have data. This is not in our imagination. We may call it different names, but there is indeed something that comes out from beta decay. They have finite mass. Yeah, so in this sense, this is reality. This is not in reality. The beta decay exists. We have a tritium atoms. The tritium atom can turn into helium-3, giving out something that doesn't interact, and that is called objects. We call it neutrinos, and we have evidence that this neutrino is not massless. So this is not an illusion. This is a reality, and this reality is supported by very hard, very compelling evidence, experimental evidence, very measurements. It's not some very famous person say, and then it is a reality. So I hope if this is the question, I understand the question, that this is the answer, or you may specify more.
So thank you, sir. So we have another question. Can you please elaborate a bit on how you connected Neutrinos with
Say it again. How what?
Can you please elaborate a bit on how you connected Neutrinos?
Oh, I'm afraid I missed some of the words. Maybe you talk slowly again, and then you are talking about how is something connected with neutrinos. Say it again.
I have
Repeat the questions.
Okay, so can you please elaborate a bit on how you connected Neutrinos?
How I connect major one mass? What?
Majorona.
How I connect? Okay, how I connect Majorana mass with neutrinos?
Yeah.
Okay. So the question is how to connect Majorana mass with neutrinos. So now this question is not in our understanding is not so exact and valid. So neutrino is an object that exists and it has mass, but we do not know whether neutrino and its own any particle is the same thing, only of different spin. If it would be the same object, only we say so an object, this neutrino, flip its spin, it becomes its anti-neutrinos, then it would becomes it is called a Majorana particle. If neutrino and anti-neutrinos are different, then that is called a direct neutrinos. In the theory, there are different ways to slightly different ways to write its mass in that famous formulas that I try to show. So this is called the mass. So a Majorana neutrino is called Majorana mass and then direct mass. But this is not fundamental. This is only a name to characterize that this term in that total Lagrangian would describe a Majorana neutrinos or describe a direct neutrinos. So neutrinos at this point we don't know whether the neutrino is Majorana or direct, and so both Majorana mass term and then direct mass terms are allowed. We hope that experiments in the future, for instance, double beta decay, would see Majorana would exist, and this is consistent with that. The Majorana neutrino mass term would be consistent with what gives us the neutrino oscillations. And we know that neutrino is Majorana term exists, and that direct mass term doesn't exist, or it's smaller than a certain value. So this is how we approach the problem.
Sir, so thank you, sir. So we have another question. This may be the last question. So related to the cool down question, that means he has asked another question, cool down. So do you mean the time translation symmetry is somehow broken there? So he has connected this question with the previous question. So related to the cool down question, do you mean the time translation symmetry is somehow broken
Most
there?
of our interactions at the microscopic level, two electrons going, is time symmetrical. Except that some weak interactions there are some minor, there are some smaller scale, smaller asymmetry there. In microscopic description, that is symmetrical. So which means that there is also which means that microscopically things can get reversed, but our universe goes in one direction. This is an error of time, because there's another fundamental quantity, a concept called entropy. The entropy would keep increasing. So it's getting more and more. It's like when an egg got broken, it is difficult to put it together. Although microscopically it can be done. So there is an error of time as far as our experience is concerned. But for microscopically, an interactions is symmetrical. Its time can be time reversed. So you have to, or the error of saying that a broken egg, can it be turned it back to an egg? In principle, it can be done, but then you have to do a lot of work and then a lot of coincidence to patch it up together. And then in the physics language to describe that is that there's an entropy concept here.
So thank you, sir. As there is no more questions, so we can conclude our discussion session, sir. So thank you. So it's a great webinar with you, sir. And I think students have learned a lot of things about neutrino physics and their detection. So and they have enjoyed lots with your slide also. So we'd like to say thanks again, sir, on the behalf of the Department of Physics, Pabna University of Science and Technology. Hopefully in near future, we will arrange another webinar with you, sir. And hopefully in near future, we can collaborate in research also, if you allow us. So thanks again, and bye for today. And hopefully,
okay,
we'll
thank you, Professor Das. And then I appreciate much your invitation and the opportunity for us to give this talk. And I think that your efforts to host and organize the seminars would be appreciated by the community, and that is a very innovative way, very timely ways to promote science to students this way. And I can predict, I'm sure that after the COVID era, there will be more and more occasions like this, that a lot of universities would or higher learning would use these methods for as scientific exchanges or educations and so on. So you are, in this sense, you are one of the pioneer. Yeah. And I wish all the students here all the best, and then and I hope that you get some inspired and go home, and then at least at the next time you heard about neutrinos in the news, so you know what it is, or some motivated ones of you can even go to the library and then dig through some more informations and keep enjoying science. And some of you would like to turn professionals later on. Yeah, certainly a good option. Yeah.
Thank you, sir. Yes. So your actually motivational speech actually encourage us and encourage our students. So thanks again. So hopefully, I definitely after COVID, we'll arrange a face-to-face session with you. So thanks for that, and thanks for everything, sir. We are really glad actually, and really proud to host you in my international
Okay.
physics.
Okay.
webinar.
So
Thank you,
so
sir.
bye bye. All the
And
best
see
to
you
you.
again.
Good luck.